Hey guys, 8-7 exponential functions. I just turned off the slate, so I need to turn that back on. We are going to be evaluating exponential functions, and we're also going to graph these exponential functions. Good stuff, right? Example 1. Okay, an exponential function, first and foremost, let's go over that, is not that one. Here we go. Can be written in the form y equals a times b to the x. Now, if you remember from 8-6, very similar to the geometric sequence. The only difference, the only real difference, is the fact that you're not subtracting 1 from, oh, from your power. All right, let's go ahead and take a look at this example. We have evaluate each exponential function, y equals 3 to the x power, for x's 2, 3, and 4. This is super, super easy. You guys have done this before, right? So when x is 2, then you have y equals 3 squared, because that's where that 2 is going. It's going in for that x. When x is 3, you've got y equals 3 cubed. When x is 4, you have y equals 3 to the 4th. Now this does say to evaluate, so you do want to give numeric the numeric representation of this. So this is going to be 9, this one is going to be 27, and this one is going to be 81. All right? Okay, so that is the answers. When x is 2, y is 9. X is 3, y is 27. When x is 4, y is 81. All right, now B is essentially the exact same thing. They're just presenting it to you in a slightly different, more pretty, in math terms, more, I don't know how to explain it, tongue-tied, just in a prettier format, if you will. This P of Q is the same as Y. This 3 goes there, times 4. This Q is the same as the X. So it's the exact same thing that we looked at up here. And when it says domain, this just means your X equals, right? So promise you, not hard there. All right, so now let's go ahead and simplify these, or write it out and simplify, I should say. Oh, goodness gracious. Okay, so we have when x is -2, we have y equals 3 times 4 to the -2. When x is 3, we have y equals 3 times 4 to the +3. So we're replacing that x, that variable, with our value for x. Now this negative here should be screaming, waving a flag at you. This tells you to flip your base. I apologize for the letters going uphill. I'm not sure how to correct that. Maybe I figured it out. So we're going to do 3 times 1 over 4 squared, because you're going to flip this over the fraction bar. And now you have, oh, we've already done that too, so we're good. 1 over 4 squared. 4 squared is going to give you 16. So we have 3 times 1, which is 3, and 1, because that would be over 1. 1 times 16 is 16. So when x is -2, y is 3/16. I want it in fraction form. I do not want it in decimal form. Okay, for the second part, y equals 3 times 4 to the 3rd power. So that's going to be 3 times 64 That's one that we use an awful lot in Algebra 2. So you might not know it by heart now, but you will someday. 3 times 64 is going to give you 192. So when your domain is -2, your range is 3/16. When your domain is 3, the x is 3, your range or your y is 192. All right, word problem. Suppose 2 mice live in a barn. If the number of mice quadruples every 3 months, so it's quadrupling every 3 months, how many mice will be in the barn after 2 years? So we're starting off with 2 mice. We have the form y equals a times b to the x. A is what we are starting with. B is the growth rate. And x is the number of times it has quadrupled or whatever. In this case, it's quadruple. All right, so starting amount. We start off with 2 little bitty mice. Our growth rate, we are quadrupling every year. So this is going to be 4. And now it says it's 4 every 3 months. I'm going to put this in parentheses. And then over the course of 2 years, how many times is this guy, or how many times are these going to quadruple? So every 3 months means 4 times a year. There's 2 years, so x would be 8. All right, setting this up, we have y equals 2 times 4 to the 8th power. Using the calculator, because I have no idea what 4 to the 8th power is, I think it's timed down on me. All right, let's see. Here we go. And it's not covering that equation. So we have 2 times 4 raised to the 8th power. And that gives us 131,072. So we have 131,072 mice. Now, I know that seems completely ridiculous, but this would be assuming that none of them have died or ran off, that they've all lived, and that they each quadruple every 3 months, that there's been no interruption in the reproduction cycles. All right, example 3. Graphs of exponential functions. We are going to use our good old-fashioned T-chart here. X, Y, use the favorite 5, -2, -1, 0, 1, 2. Remember, and I stress this, but it still doesn't click with some, so hopefully it'll click now. You can pick whatever numbers you want here. I could put 99 and 72 and 13. I could put 0.5 there if I wanted to. It doesn't matter because you're going to be putting this number into this equation to get an output, right? So I'm going to put -2 in for x. So we have 2 times 3 to the -2. Well, this means I flip it. So then that's 2 times 1 over 3 squared. 2 times 1 is 2. 1 times 3 squared is 9, so we have 2 9s. -1. 2 times 3 to the -1 is the same as 2 times 1 over 3, because this tells us to flip it, and this is 2 over 1 times 1/3, so that's 2/3. Putting 0 in, 2 times 3 to the 0. What is anything to the 0 power? It is 1. So we have this become 1. 2 times 1 is 2. putting 1 in up here, we have 2 times 3 to the first. Well, anything to the first power is just itself, so 2 times 3 is 6. And then putting 2 in, we have 2 times 3 squared. 3 squared we know is 9. 2 times 9 is 18. All right, so now let's go ahead and graph this. We have our ordered pairs. We know where we're going, kind of. And again, this does not have to be perfect. I'm not going to get all the way up there. I was hoping I could, but I didn't. All right, so we have -2, 2 ninths. So this is -2, and 2 ninths is like, if I'm not mistaken, 0.22. So that's going to be right about there. It's going to be above the x-axis, but not by a whole lot. -1 2/3. So that's approximately 0.7. So we have -1 in that neighborhood. 0, 2, 1, 6, and then 2, 18 is going to be way up there somewhere. So your function is coming from the left, negative infinity, and it's, oh, pretend that is straight. And it is increasing infinity as it gets larger. All right? All you have to know is that you have to plot your points and then sketch your line, and hopefully you do a better job than I did. That one's a little bit better. Example 4, and this is the last one from this lesson. We have the function f of x is 1.25, models the increase in size of an image being copied over and over at 125% on a photocopier. Graph the function. Okay, now this is a real world situation, right? Because we're talking about copies, and we're talking about an image being copied. Can we have negative images? Nope. Can we have negative copies? Nope. So we're not going to have any negative x's. Let's go ahead and start with 0 because you could have 0. Let's do 1, 2, and 3. So now 1.25 raised to the 0 is just 1. 1.25 raised to the 1 is 1.25. 1.25 raised to the second power, or squared, is going to give us 1.25. Well, heavens, what did I do? It already timed out. No fair. Technology is not my friend. All right, so you've got 1.25 squared, and that's going to give you 1.56. I'm just going to write 1.56 instead of carrying that on. All right, and now we need to put 1.25 raised to the third power, 1.25 caret 3, enter. And we've got 1.95. So 1.95. All right, I'm going to go ahead and graph this. Now, my y values, the biggest I have is 1.95. The smallest I have is 1. So we can keep it relatively simple and not put the scales marks really close to each other. Make it easier on us anyway. 0 is at 1. 1 is at 1.25. 2 is at 1.56. You see, I'm just kind of guessing because this looks like about 1.5. This looks like about 25. And then 3 is at 1.95. So we would continue to go. Can we draw a line through these points? No. This is discrete data because you can't have a partial copy. You either have a copy or you don't. So this is an example of discrete data. All right, guys, that concludes it for the exponential functions. Hope it's been a good one. I'll see you later.